To the seminar about graph representations by NLP and graph clustering. Let me introduce Anton. Anton is a PhD student in our group, and he will speak today about various graph clustering algorithms and how they can be applied to linguistic graphs. Anton, welcome, and let's start.
Hello, Alexander. Hello, everybody. Let me share my screen. Do you see the collab code? Collab notebook.
Yes, yes.
Yeah, we can see.
I've sent the link to the chat, so you can open it and copy it to your Google Drive and repeat all experiments. Well, today's seminar will be about graphs in natural language processing. There are three types of most common graphs in NLP. This is word co-occurrency graph. It is a graph which represents neighborhood of words in text corpora. So the words which appeared in the same context or just sequentially in the text, they will have an edge between the nodes. Another type of graph is similarity graph. The nodes of this graph are words from vocabulary, and edges are similarity between these words. So we need some vector space or word embedding space to represent this graph. For example, word to vec or glove or BERT contextualized embeddings can be used to construct this graph. And the third graph is knowledge graph. This graph represents the relation between entities, between words based on some knowledge. For example, Wikipedia or Wikidata databases. So we can traverse this graph and find some relations like location or population, etc. Today we will work with the first two types of graph, word co-occurrency graph and similarity graph. Well, let's start from the text. We will process and analyze the graph structure of this small but very interesting text. This text is about how flies fly. Flies are insects, and this text about biomechanics and some property of their flight and aerodynamics. This text is very short, but it's interesting because a word fly have two meanings. To start with, we will pre-process this text to make it appropriate for the further algorithms. We will use regular expressions, NLTK, and collections. First of all, we need to lowercase our text to reduce the number of words and to be sure that the words in the beginning of sentence and in the center are in same meaning. Then we need to apply stemming to all words in our dictionary. Stemming is a procedure which reduces some prefixes or suffixes which are related to grammar, like ink or ed, past simple. So it also reduces the size of vocabulary and makes words more similar in different grammar context. So here we apply stemming to all words in our text. And then we need to filter the most common words. Maybe it is not very necessary for such short texts like this, but in future you will need to filter some frequent subset of words to reduce vocabulary, because vocabulary can be very large and it's a problem. Well, the next step is to delete stop words. Stop words are such meaningless words like articles or negotiations, not. So we can just delete all these words from our text. In these two lines, we create vocabulary and inverse vocabulary. These are two mappings from words to word indices, so we can create some correspondence between a word and a number. So every word have a correspondent number, and this inverse vocabulary makes the opposite. It creates a mapping from indices to words from our set. And the last step is tokenization of sentences. So we obtain a list of lists of tokens. Let me show you. Now our sentences look like this. As you can see, a word fly now looks like this. It is a result of stemming. It reduces the suffixes in such a way that in all grammar contexts, the word will be the same. But sometimes it does silly mistakes like this, but it's not a problem because we know that it's a word fly. And as you can see, these words from text were also deleted as they are stop words. Well, next. Now we will create a context matrix. It is a kind of adjacency matrix of neighborhood of all words in our sentences. We go with a sliding window through all sentences, one by one words, and put one to corresponding place in a matrix, which means that there is a connection between these two adjacent words in our text. We can plot such matrix, and we can see that our words, this is indices of our words in our vocabulary, have some neighbors. Such matrices represents the structure of co-occurrency graph. Now, when we have a context matrix or adjacency matrix, we can apply some graph algorithms. To start with, we will use hard clustering. The most common algorithm in NLP for hard clustering is Chinese whispers. It is a simple iterative algorithm which divides a graph onto clusters. And the main advantage of this algorithm is that we don't need to know the number of clusters we want to achieve. This algorithm will converge to the most appropriate number of clusters it thinks. Also, it's quite fast and works good for very large graphs. There are created implementations for such simple algorithm. We can install Chinese whispers through with pip install.
Oh, a question about the name of the algorithm, Chinese whispers. I think this name is just the name of a game. Like it's more known as telegraph game, telephone game, or corrupted telephone in Russian, where somebody passes a message to another person, and then it got corrupted, and so on and so forth. And I think the metaphoric idea was that you update the status of a class or a cluster.
Communicating with adjacent nodes.
Yeah, on the basis of just adjacent nodes. So this is, yeah, the reason. And this is actually a funny thing about this name, because this name was introduced like almost 20 names 2 years ago. And according to current, let's say, to current day, the name is not politically correct anymore. So in the new version of the algorithm, the author decided to rebrand it because, yeah, it's like,
Maybe they will be forced to rename their algorithm
yes.
in the nearest future. Thank you for your comment, Alexander. Now let's apply this algorithm for clustering our concurrency graph. So we installed the package Chinese Whispers, imported the module for working with graphs, and algorithm itself. First of all, we need to convert our matrix, our adjacency or context matrix from NumPy format to network X, to the format of this library. This is a universal format which represents graphs in a very efficient way. So we convert our matrix to an object, to a graph in this line. Then we apply algorithm, Chinese whispers, and we can print the graphs, the clusters. As you can see, there are some clusters which are kind of related to insects, and some clusters are related to flight, to a process of flight. And also we can plot this graph and see what happens. Well, not very clear, but some structure definitely is. Here is the word fly, our insect, which were spoiled by stammer, so it looks like flea, but it is fly. And it is in the center of our graph. Well, let's try another clustering algorithm, Markov clustering. This is also a very simple algorithm which can be performed in just several steps. It takes adjacency matrix and outputs a matrix of clusters. Here is structure of this algorithm. Let's first of all plot our context matrix again. Here is our context matrix of neighborhood of words in our text. The first step of the algorithm is adding self loops or self-neighboring of words to the matrix. Effectively, it looks like adding a diagonal matrix like this. So now we add such diagonal. This is needed to bring numerical stability to this algorithm. Without such diagonal, it would be problematic to perform the following steps. But this diagonal doesn't have much sense. It's just a neighboring of the words to itself, self loops. The next step is normalization. We need to normalize the columns of this matrix so that they were summarized to identities, to ones. This is a function for normalization of columns of a matrix. And the algorithm itself, it is very short and very simple. Iteratively repeat normalization, and then expansion and inflation. Expansion, it is matrix power. So we just take a power of a matrix. Then we do inflation. It is a kind of element-wise power. So matrix power isn't element-wise power. It is a complex linear algebra operation, which can be do with NumPy lenalc module. So this is expansion, and this is inflation. Inflation is just element-wise power of matrix. Then normalize again and repeat. Repeat until convergence. There are no any mathematical guarantees that it would converge, but usually it converges. Well, let's apply these functions to our matrix. Well, here is clusters. We can see that there are some big clusters, one big cluster and some small clusters. Now we create again a graph object with network X module from this adjacency cluster matrix. And now we can plot our graph structure. Well, here is our graph and clusters. I see that the red part is a kind of flight relation words. And it seems that yellow is about insect, but I'm not sure. Fruit, fly, dead, wing, insect. Kind of work, but not clearly. Well, next. The previous two algorithms were about hard clustering. Hard clustering is a situation when we put only one cluster, assign only one cluster to each node of a graph. So it is like a situation on the left of this picture. Our clusters can't intersect, but sometimes one word can have several meanings and can be assigned to several clusters. This situation is described with soft clustering. At soft clustering, clusters can intersect with each other, and one node can be assigned to several clusters simultaneously. Let's talk about algorithms for soft clustering. One of the best algorithms is what's set. It's not thoroughly algorithm, it's a meta algorithm. So it uses some more shallow algorithms like Chinese whispers and Markov clustering and apply over them another procedure to retrieve soft clusters and different meanings of words. This algorithm is implemented in JavaScript, in Java, and can be downloaded from GitHub. So we just download this jar file. This jar file, this algorithm takes as input a matrix, a file in a very special format. This format you can see here. A pair of words separated by tab and a weight of edge connecting these two words. So in this cell, we create such file from our adjacency matrix and then write it to our Google Drive. Now we can apply what's set algorithm with command line syntaxes. We use this sign to send this code to command prompt. It takes as input our created file, graph.txt. We created this file here, and it looks like this, and applies what's set algorithm with Chinese whispers as the shallow algorithms for clusterization. Well, the result of the algorithm was saved to output TSV file. Now we can read this file with pandas. And look what happens. Well, this is the first row. It was displayed like a header of data frame, but it is the first cluster and other clusters. So we can see, for example, a word fly is assigned to several clusters. This cluster, this cluster, this cluster. It doesn't seem to me that it worked well, but it did some soft separation of clusters, some soft clusterization. Maybe hyperparameters of clusterization algorithms are not very well, or just the text is too small for this algorithm. Okay, let's go next. Or do we need to make a break, maybe?
Yes, maybe let's make some small break now. Let's start at 4 o'clock, 45 minutes then, in 7 minutes. So this one?
Okay.
Okay.
Well, let's continue. So this part is about um, word vectors, word embeddings, and similarity graphs. I'm sure that most of you know about what is word vectors, but I will repeat. Well, due to distributional hypothesis, we can represent words through the frequencies of another words in the context of these ones. So we can create some vector space uh, where we can map all words, and the semantic similarity of these words will be saved in this space. So if two words are similar semantically, like for example, like man and boy, these two words will be similar also in word vector space. And there are some interesting properties of this space, as we can apply some standard linear algebra operations like um, summation, subtracting of vectors from each other, and computing cosines between these vectors. As you can see on this picture, the difference of vector king and queen is very similar to difference of man and woman. So we can just make something like this. Vector of man plus vector of queen minus king, we can obtain vector of a word woman. There are many pre-trained vector spaces, many pre-trained models for obtaining vectors of these words. We can just download a lookup table of these words, of these vectors. The most popular and easy to use library for word vectors is GenSim. We can install GenSim through pip, then import downloader API, through which we can download lookup table for pre-trained word embeddings on this data set. This number means that these vectors will have dimensionality of 50. Let's wait a little. It will take about a minute to download these vectors. So this lookup table is a kind of dictionary which helps us to map a word to its vector. For example, like this. So let's wait until the downloading finished. Okay, here is a vector representation of a word man. Now let's play with 1000 most popular, most common words in English. We can download this list of words with this link through WeGet. And then calculate word embeddings for these words. These words are most common, like chick, deer, enemy, teeth, etc. Now let's calculate word embeddings for all these words. At this line, we iterate through our list of most common words. It is our downloaded list of words, 1000 words, and calculating or extracting vectors from lookup table. So here we just extract our word vectors. Then we need to normalize these vectors because these vectors are not normalized to 1. Here we iterate over all vectors in our list and normalize them by dividing on their L2 norm. Here we can see that we now have a matrix of shape about 1000 and 50. This is a matrix of word vectors for most common English words. Now let's do dimensionality reduction of these vectors. TSNE method is a manifold method, manifold machine learning method for reducing dimensionality of data. We can squeeze our vectors from dimensionality 50 to dimension just 2 dimensions, trying to preserve all relations and similarities of pairwise distances on words. Now we can plot this. Here you can see our 1000 vectors squeezed to dimension 2 with TSNE method, and they kind of clustered into some small islands. We can do interactive plot of these squeezed vectors and look what words represents. For example, at this small cluster, there are some geographical words: valley, lake, river, mountain. This cluster, food, corn, drink, sugar. Okay, here something strange. Sister, wife, mother, lady, her, miss. Quite interesting. We can see that using word vectors, such kind of semantic vector space of words, we can map them on a 2D, two-dimensional surface and to observe the relations of words on just an image. Okay, now let's do a kind of clusterization algorithms for our similarity graph. To compute a similarity matrix, we need to compute a Gram matrix. It is a matrix of pairwise similarities of vectors. So here is a vector matrix. If we multiply it on its transpose, we will achieve a matrix of pairwise distances of words. So this matrix is a matrix of pairwise distances. Here we set our diagonal to 0, and we can plot our similarity matrix. This matrix represents a fully connected similarity graph with edges of weight equal to similarity between nodes, similarity between edges. To make it more readable and reduce the number of edges from fully connected to some smaller set, we can binarize this matrix. We just leave only those elements which are larger than 0.94, or we can put any number from 0 to 1 here. And now we make these elements equal to 1, and all other elements are equal to 0. So these are the most strong, the most highly correlated words in our set of 1000 most common words. So we left only most strong edges from our fully connected similarity graph. As you can see, there are a few dots here, and mostly it is 0. This is our new adjacency matrix based on similarity graph. Now we can convert this matrix, this adjacency matrix, to network X object, to a graph object, and plot it as a graph. Okay, here we can see some graph structure of our words. For example, here is a cluster of numbers. They're very similar to each other according to word-to-vector linear space. Here is some modular verbs. Here are some words also. So definitely there is some graph structure here. Okay. Now we can apply our clusterization algorithms. I'm sorry. Something wrong here. Okay, let's apply this. Let's create a similarity graph for our previous small text about flies, and plot this graph and clusterize it. So let's again preprocess the text about flies. Then compute word vectors for all words from our text. Now we squeeze the dimensionality of our vectors to 2 dimensions with help of TSNE manifold method. Now let's interactively plot it. Well, okay. Here is our words from text about why flies, which are mapped to vector space and then squeezed to do 2D dimension space. Okay, some clusters. Quite reasonable, I think. Now let's create a gram matrix, a matrix of pairwise distances between our word vectors. Here is our gram matrix of pairwise distances. Now we binarize this matrix. We leave only the most strong edges between words in our text. Convert it to network X graph object and clusterize. So here is clusterization. Proposed measure, fly, insects, wings, and one huge cluster. Doesn't look very reasonable, but maybe we should tune some hyperparameters like binarization parameter. No, too high. Too small. Only one cluster. Okay. So this is clusterization method of word similarity graph. We create a vector space for words from our corpora, then create a gram matrix, a pairwise similarity of these vectors, then binarize this matrix. It becomes adjacency matrix of our graph, and then we apply our algorithms to this adjacency matrix. It may be Chinese whispers or Markov clustering or what's it. And finally, here is another text, quite large, about power. So this text consists of sentences with different meanings of a word power. Let's repeat some algorithms with this text. Okay, so now text equals this. Now we go up. Again, tokenize. Context matrix. Small words, I think. So here is a context matrix of 300 most common words from this text. Now we apply Chinese whispering algorithm to it. Here are some clusters, and let's plot them. Wow, too many words to understand any cluster structure. Maybe we need more iterations.
What was the word which target these sentences contained actually?
As far as I remember, a word power. So this.
Okay, yeah, but maybe we can do like this. We can in the pre-processing remove the word power.
A word power.
Yeah, so if we remove the word power, maybe it will be better, because the word power usually, or the ego of this network should be removed, because this will link everything, right? So because the word power will be co-occurring with all words in all meanings. So this is kind of a stop word. Or
no, it's not power, it's about control.
Control, okay, yes.
Control.
Then in this case, I suggest to remove all flexions of or the word control and all versions of the word control. And then what we might expect is that different words co-occurring in control with different senses are going to be separated. Let's say we have control like in a dynamic system control, something like this, and the words like dynamic system or its synonyms, they will be grouped together, and maybe the words which are related to management or something like this will be grouped together. Because if you leave the word control, it might be hard to.
So just connects all clusters together and
exactly, yeah. So
separating.
so by just by definition, it will connect everything together.
Okay,
any
let's
kind of clustering very hard.
let's do it here. So we just subtract a word control from our word set. Here, just word set equals word set minus set of words consisting just of one word, control. Okay, now it should work. As you can see, now there is no two big lines here, because without this deleting, there were very strong correlation of this word with all another words. So just let's.
Yeah, can you show it once again? That's interesting.
Sure, I'm doing it. Not another text about flies again. This text. No. Without extracting control, word matrix. Here it is. With word control, you can see these two strong correlated lines, as word control correlates with all other words, because this text is about meanings of control. And if we subtract this word from our corpora, now these correlations disappear.
So okay, maybe let's try then to see this, how these new results will look like. By the way, how many sentences there were in this text? Because you show that it was like a one very long line, but just to understand how many data we have in this thing.
About several thousand words. Two small steps, I guess. It's only 20 steps of algorithm. Let's apply and plot the graph. Too many words. We can reduce our vocabulary, for example.
Maybe we can try to increase the threshold, because now it seems that this graph is just like a click, right? So so if we increase the threshold, also the graph is going to be more sparse, and only the strongest connections will remain. So that okay. So you take 300 most common words.
Yes.
What is this? This a word to vec or? No,
most common just
occurrences, right?
Occurrences, yes.
Okay, yeah. So
we count on words, and
this is another problem, I think, because you need to keep maybe at most like 30 or maybe. So we try 30, because 300 it's like a lot too much. Yeah.
Okay, let's try 30. Applying algorithm, and it has only one cluster.
But how many sentences you have? Maybe it's just fast. I'm sure it is the right data.
Do you want to see the text?
Yeah. You mean this text about control, right?
Yes, this text is about control.
You concatenated many texts here, right?
Yes, just with dot and space.
Can you split to see how many texts you have there? Maybe like
Tokenized sentences, we can
yeah, just
see the length of our list.
mhm.
94 sentences.
Okay, hundreds of sentences. Yeah, then maybe let's see if you keep this 100 threshold. And then maybe playing with the threshold. Okay, that looks a bit more reasonable, but okay, what do we have here? Because company must power, and then I think yeah, okay. Yeah, something like about political control, I think, like New York, and then
And controlling
uh,
hours, games.
capital, yeah, and then
Let's try microclustering
yeah,
for
okay,
this
I'll
set
try
of words.
another version to see how it is. But this Markov clustering, you have the word control also inside it, or it's
Without it,
out?
without word control.
Okay.
Okay,
Yeah, so that looks a bit more coherent. So I will go into open WordNet and see what census actually they proposed. WordNet. Uh, yeah, I can send the chat this link, and maybe you can open it and see what possible census we might have. So, so this was the control for, as noun, right? These sentences.
yes, control as noun.
You can open the link in the chat.
Yes, sure.
I see that there is a first sense of control is a power to direct, and the second sense measures the control of disease, and then regulation of maintenance of function. So maybe these senses are a little bit too kind of generic, maybe for Vicimos to be able to easily distinguish between them. So I would say that the problem of word sense induction is that it's going to separate what we call homonymous senses. So let's say Python is a programming language and Python is snake. You will have very clear separation. If you have some less clear or related senses, like Java as a programming language or Java as a platform, they go into co-occur with the same words, and it might be more difficult to distribute between them. Okay, but Anyways, thanks for this demonstration. And yeah, do we have some more examples or which?
No, that's all. If you have any questions or if you want to go through some algorithms again, I can do this. So any questions
Okay, yeah,
from the
then
audience?
please type the question or let us know if you're curious about some part of it. Okay, so the people ask for your Telegram, so that might be a good idea if people they are going to students are going to finalize their projects, and maybe if somebody is going to use some of these technologies in the pilot project, for instance, some other projects, so that would be very, very helpful. Okay, thank you very much. Then let's conclude this session. Thank you, Anton, for this nice demonstration of what clustering can do for
Thank you
us.
for your attention.
And yeah, thanks for everybody for coming, and have a nice evening. Bye bye.
Goodbye.